Let me begin with the story. According to a well-known legend, a young schoolboy named Carl Friedrich Gauss, later regarded as one of the greatest mathematicians in history, was once set a task by his teacher. The question was simple. What's the sum of the integers from 1 to 100? The teacher had intended it as a time-consuming exercise, expecting the class to add each number slowly by hand, one by one, all the way up to 100. But Gauss responded almost instantly with the correct answer, 5,050. His method was elegant. He began by imagining all the integers between 1 and 100, and then quickly realised that the numbers could be paired from opposite ends of the sequence. If you then take the first and last numbers, 1 and 100, they add up to 101. So do 2 and 99, 3 and 98, and so on. Each pair gives the same total, 101. And since there are 50 pairs, you simply need to multiply 50 by 101 to get an answer of 5,050. And this is the answer that Gauss found in a matter of seconds. This clever trick leads directly to a general formula. If you want to sum the first n integers, and in our example, n was 100, you take the number of terms and divide by 2 to get the number of pairs, which was 50 in our example, and then multiply by n plus 1, the value of each pair when added together, which was 101 in our example. The result is n times n plus 1 divided by 2, and this formula gives the exact sum of the first n terms. But now let's take the idea to its limit. What happens if we try to add all the positive integers, not just up to 100 or 1,000, but to infinity? Using our general equation, we can clearly see that as n gets larger, the total also increases, and it grows rapidly as the number of terms increases. This becomes especially clear if we plot the number of terms on the x-axis and the total sum on the y-axis. The result is a curve that grows quadratically for large values of n, and this tells us something important. As we take the number of terms summed to infinity, the total sum will also tend to infinity. So while Gauss's trick worked perfectly for summing any finite sequence of integers, it also reveals that the infinite sum of all positive integers doesn't settle down to any fixed value. It increases without bound. In the language of mathematics, we say that the sum of the positive integers diverges. It grows without bound. And this aligns with our intuition. If you ask someone, why does the sum diverge? They'll likely say, because each number is bigger than the last. And they'd be right. But now let's turn that idea on its head. What if, instead of adding larger and larger numbers, we added smaller and smaller ones? Could an infinite sum of decreasing terms actually converge? And that brings us to a fascinating question. What if we take the same positive integers 1, 2, 3, 4, 5, 6 and so on, but instead of adding them directly, we add their reciprocals? This is known as the harmonic series, and at first glance it seems very different. The numbers we're adding are getting smaller and smaller. We can visualise this by plotting the cumulative sum, and we see that each additional term contributes less than the one before. And if we then plot the cumulative sum up to the first 200 terms and sketch a smooth curve through the points, it appears to grow steadily. Extend it to the first 2,000 terms and it starts to look like the curve might level off. The growth is so slow, it tempts you to believe that the total may be approaching a limit. And to emphasise just how slow, to exceed a total of 5, you must add the first 83 terms. To get past 6, you must add 227 terms. To reach 10, you must add over 12,000 terms. And to reach 20, you'll need more than 250 million terms. So surely this series must converge. Or does it? This is where a 14th century French scholar named Nicole Orzma enters the story and delivers a beautiful and surprising answer. His argument is simple, intuitive, and centuries ahead of its time. Orzma began by writing out the harmonic series, and then he noticed something truly clever. He grouped the terms in a specific way. The first group contained just the number 1, the second group contained 1/2, the third had 2 terms, a third and a quarter, the fourth had 4 terms, a fifth, a sixth, a seventh and an eighth, and the fifth had 8 terms, running from 1/9 to 1/16, and so on, with each subsequent group doubling in size. And here's where the insight really shines. Take the third group, a third plus a quarter. If you think about it, this is greater than 1/4 plus 1/4, which means that a third plus a quarter is greater than a half. In the fourth group, each of the 4 terms is greater than or equal to 1/8, so the total is more than 4 times 1/8, again over 1/2. The fifth group has 8 terms, each greater than or equal to 1/16, so the sum is more than 8 times 1/16, once again more than 1/2. And this pattern continues. Each group adds more than a half to the total. So Orzma concluded that the entire harmonic series must be greater than 1 plus a never-ending stream of halves. 1 plus a half, plus a half, plus a half, and so on. And we can visualise this. If we plot the accumulation of those halves, we get a perfect steady staircase, rising without end. But Orzma showed something remarkable. The harmonic series doesn't just follow this staircase, it outpaces it. It climbs even faster. And that's the punchline. Even though the terms in the harmonic series get smaller and smaller, the total still grows without bound. Orzma had shown that this seemingly gentle series does not converge, it diverges. Okay, so let's pause. We've now seen 2 infinite series that diverge, the sum of the positive integers and the sum of their reciprocals. And this naturally raises a tantalising question. Are there infinite series that do converge? And can you really add up an infinite number of terms and arrive at a finite result? And if so, how? This was exactly the kind of question that fascinated mathematicians in the late 1600s, a time when the idea of infinity was being pulled, stretched and reshaped by the newly emerging language of calculus. One of those figures was Christian Huygens, a Dutch physicist and mathematician at the very centre of Europe's scientific revolution. And in the early 1670s, he crossed paths with a young German diplomat named Gottfried Wilhelm Leibniz, a child prodigy who had entered university at 15, completed his doctorate by 20, and seemed destined for greatness. Leibniz wasn't travelling for mathematical purposes. He'd been sent to Paris on a diplomatic mission, working in the service of the Elector of Mainz, one of the many rulers of the fragmented German states. But fate had other plans. During his time in Paris, Leibniz sought out Huygens, and that meeting would change everything. Huygens quickly recognised Leibniz's brilliance and became an informal mentor, introducing him to the latest ideas in mathematics and physics. And among the problems he posed was a deceptively simple question. What happens if you sum the reciprocals of the triangular numbers? Okay, well, first of all, what are the triangular numbers? To picture them, imagine arranging circles into rows to form a triangle. 1 circle in the first row, 2 in the second, 3 in the third, 4 in the fourth, and so on. Now, if we count the total number of circles up to each row, we get a sequence. The first row has 1. The first 2 rows added together makes 3. The first 3 rows give 6. And then 10, 15, 21, 28 and 36. These totals, the running sums of the rows, are the triangular numbers. Now, mathematically speaking, the nth triangular number is given by n times n plus 1 divided by 2. But Huygens wasn't interested in the triangular numbers themselves. He wanted to know what happens when you take the reciprocals of those numbers and add them all together. Not just a few of them, all of them, an infinite number. His question was simple and profound. Does this sum converge? And if so, what does it converge to? Okay, but how on earth do you add infinitely many fractions? For most people, the problem would seem impossible, but not for Leibniz. he spotted something almost immediately. He began by writing out the first few terms of the sum, and then dividing every term in the sum by 2, and he ended up with the following expression. And he then noticed something rather remarkable. He realised that each of these terms could be rewritten using a clever trick. The first term, 1/2, could be written as 1 minus a half. The next term, a sixth, could be written as a half minus a third. The next as a third minus a quarter, and then a quarter minus a fifth, and so on. And now let's imagine adding all of these terms as written, one after another. And so, using this trick, Leibniz was able to rewrite the series in a suggestive way. But now comes the genius. If you simply remove the brackets and lay out the terms in full, something beautiful happens. After the initial number 1, every term begins to cancel with its neighbour. The minus half cancels the plus half, the minus third cancels the plus third, the minus quarter cancels the plus quarter, and so on. Each negative term cancelled out by the positive term that follows. This continues all the way to infinity. Everything vanishes except that very first term. And so we're left with s divided by 2 equals 1. And this means that s must be equal to 2. And so, in a single elegant stroke, Leibniz had shown that this infinite series, the sum of the reciprocals of the triangular numbers, converged. And not just approximately, but exactly. The total wasn't some messy decimal or a rough estimate, it was the clean, simple number 2. Leibniz had done something remarkable. He had found the exact sum of an infinite series. Not just an approximation, but a clean, elegant result. And once you have one example like that, it's hard to stop. Mathematicians became obsessed with the idea. If the sum of the reciprocals of the triangular numbers could be tamed, then what else? Could even more complex infinite series be solved? Could others be shown to converge, or even better, be reduced to a neat, closed-form answer? Among those captivated by these questions were two brilliant brothers from the city of Basel, Switzerland, Jacob and Johann Bernouilli. Jacob, the elder, helped lay the foundations of probability theory. Johann the younger was a passionate advocate of Leibniz's newly invented calculus and co-authored the first textbook on the subject. They were geniuses and fierce rivals. Each tried to outshine the other, and both were obsessed with the mysteries of infinite series. In fact, both independently proved that the harmonic series diverges, with Johann providing an ingenious argument that built directly on the reciprocal triangular number series that Leibniz had just summed. But soon their attention turned to a deeper puzzle, a series that looked harmless, even friendly at first glance. But the more you stared at it, the more it refused to yield. This time, the focus wasn't on triangular numbers, but on square numbers, values like 1, 4, 9, 16, 25, etc. You can think of the square numbers as the result of squaring the natural numbers. So 1 equals 1 squared, 4 equals 2 squared, 9 equals 3 squared, 16 equals 4 squared, and 25 equals 5 squared, and so on. And you can also visualise the square numbers. Imagine arranging dots or circles into perfect squares. 1 circle makes a 1 by 1 square, 4 circles makes a 2 by 2 grid, 9 circles forms a 3 by 3 grid, and 16 circles a 4 by 4 grid, and so on. Each square number creates a perfect square of dots. Simple, predictable, beautifully structured. Now, the question that demanded an answer was this. What happens if you take the reciprocals of these square numbers and then add them all together? Not just a few of them, all of them. An infinite number. And then the natural question is, does this converge to a finite value? And if so, what exactly is that value? That was the mystery that required a solution. And in his 1689 treatise on infinite series, Jacob Bernouilli made the first serious attempt to tame this beast. He couldn't find the exact sum, but he had an idea. If he could find another infinite series that he knew converged, and then show that every term in the reciprocal square series was smaller than the corresponding term in that convergent one, then he could conclude that this series is convergent. It was a clever strategy, and as luck would have it, such a series already existed, the one that Leibniz had just solved. If you recall, Leibniz had shown that the sum of the reciprocals of the triangular numbers converged exactly to the number 2. And so Jacob's strategy was to compare this with the sum of the reciprocals of the square numbers. So let's do that. If we line up the two series side by side and compare their terms, something becomes immediately clear. A quarter is smaller than a third, a ninth smaller than a sixth, a 16th is smaller than a 10th, a 25th is smaller than a 15th, and so on. We can see that every term in the second series, the reciprocal square series, is smaller than the corresponding term in the triangular reciprocal series. And we can visualize this. If we sum the same number of terms in each series, the total will always be greater in the reciprocal triangular series than in the reciprocal square series. As the plot shows, the triangular series outpaces the square series at every step. So if we keep adding more and more terms, the total for the square numbers will always lag behind. And since we know that an infinite number of reciprocal triangular numbers sums exactly to 2, it follows that the infinite sum of the square reciprocals must be less than 2. But although both Bernouilli brothers knew the series converged, and that it converged to a number less than 2, they had no idea what it converged to. No pattern emerged, no clever trick seemed to work. Jacob himself admitted defeat, writing, "If anyone finds and communicates to us that which up to now has eluded our efforts, great will be our gratitude." With that public challenge, the problem took on a life of its own. Mathematicians across Europe tried and failed to crack it, and because the mystery was first proposed by Jacob in his hometown, it became known as the Basel Problem. So who did eventually solve the puzzle? Well, here's the beautiful twist in the story. The person who finally cracked the Basel Problem turned out to be, by many accounts, the greatest mathematician who ever lived. And remarkably, his story begins with the Bernouillis, because history would have it that his first teacher and mathematical mentor was none other than Johann Bernoulli himself. The student's name? Leonhard Euler. Euler was born in Basel, Switzerland in 1707, and from a young age his brilliance was unmistakable. His father, recognising his son's talent, arranged for weekly meetings with Johann Bernoulli, who quickly realised he had a prodigy on his hands. By 19, Euler had already won an award from the French Academy. By 20, he had secured a position at the St. Petersburg Academy in Russia. He would later move to Berlin, and then he returned to St. Petersburg, where he remained until his sudden death in 1783. To call him prolific is an understatement. Euler's collected works, known as the Opera Omnia, span 73 volumes and include around 866 publications, books, articles and treatises written in Latin, French and German. His output was so immense that unpublished papers continued to appear for 47 years after his death. But sheer quantity doesn't begin to capture it. A quick browse through the online Euler archive reveals the true nature of his genius. Paper after paper bursting with insight, elegance and originality. He laid the foundations of graph theory, complex analysis, number theory, the calculus of variations and differential equations, shaping vast areas of modern mathematics. And it was Euler who, early in his career, set himself to the task of solving the Basel problem, a problem that had stumped the Bernouillis, Leibniz and many of Europe's finest minds. Now, one way to approach this problem, at least to get a feel for it, is to calculate terms of the series manually and try to spot a pattern or guess what it might be converging to. For example, if we sum the first 5, 10, 15 or 20 terms, we see that the number increases but at a decreasing rate. If we plot this, it's clear that the sum climbs slowly, creeping ever closer to some mysterious number. But what number? That's the question. And adding just 20 terms certainly won't reveal the final answer. You might imagine that adding more and more terms would bring you closer, and in principle it would. But it's completely unreasonable to keep going indefinitely. This was the early 18th century. No calculators, no computers. Even subbing 20 terms by hand was laborious. 100? Difficult. 1,000? Out of the question. And yet, in 1731, Euler estimated the sum to 6 decimal places, finding a value of 1.644934. He didn't get there through brute force. This wasn't mindless arithmetic. It was mathematical ingenuity, clever transformations, rearrangements, and a deep intuition for how infinite series behave. And Euler was aware of just how extraordinary this was. Referring to his 6 decimal estimate, he wrote, "If anyone should wish to determine the sum of this series by adding terms from the beginning, more than 1,000 terms must be added in order to obtain the number I have found." However, despite his astonishingly accurate approximation, he didn't yet know why this number appeared, or where it came from. But he didn't give up, and in a stroke of genius that has become legend in the mathematical world, he found a path. An approach so bold and so beautiful that it remains one of the most remarkable mathematical insights ever recorded. In his notes, Euler scribbled, "Quite unexpectedly, I have found an elegant formula depending on pi, and it is this result, Euler's extraordinary leap, that we will now explore." To understand how Euler arrived at his answer, we'll need to explore a few simple but powerful mathematical ideas, beginning with something familiar to every student of trigonometry, the sine function. As you might recall, the sine function arises in the context of right-angled triangles. If we label an angle x, we can then identify the adjacent, opposite, and hypotenuse of our right-angled triangle, and then the sine of x is defined as the ratio of the opposite side to the hypotenuse. We can visualize how this ratio changes as the angle x changes by imagining a hypotenuse of unit length forming a right triangle inside a unit circle. As the angle x increases, the tip of the hypotenuse traces a circular arc, and the ratio, the sine of the angle, traces out a smooth wave-like curve that oscillates between +1 and -1. If we look at this curve, we see that sine of x equals 0 whenever x equals 0, plus or minus pi, 2 pi, 3 pi, etc. radians. In other words, the sine wave crosses the x-axis at regular intervals, at every integer multiple of pi. Now, to understand how Euler found the exact sum of the Basel problem, we need to explore how certain functions, like sine of x, which we've just looked at, can be expressed as infinite polynomials. This is one of the most beautiful and powerful results in all of mathematics, the Taylor series. Let's say that we have a smooth function f of x, and we want to approximate it near x equals 0. We might guess that it could be written as a polynomial of the following form, where a0, a1, a2, etc. are coefficients. But how would we figure out what these coefficients are? Well, we want this polynomial to match the function, not just at x equals 0, but also in how it behaves near that point. That means matching the slope, the curvature, the bend of the function. In other words, we want the polynomial's value and all of its derivatives to match the functions at x equals 0. So let's work it out. We start with our polynomial expression and then consider the first derivative, which we'll denote as f prime, where we see that the derivative of a1x is just a1, the derivative of a2x squared is 2a2x, the derivative of a3x cubed is 3a3x squared, and so on, using standard differentiation rules. Next, we differentiate again to get the second derivative, and one more time to get the third derivative, which we write as f triple prime. And we could imagine continuing this process for higher order terms. Next, if we evaluate each of these derivatives at x equals 0, we find the following expressions. And if we then rearrange these, we can express the coefficients a1, a2 and a3 in terms of the derivatives of the function evaluated at x equals 0. Now here's something interesting. The denominator of a2 turns out to be 2 times 1, which is just 2 factorial. The denominator of a3 is 3 times 2 times 1, that's 3 factorial. For a4 it's 4 factorial, and the pattern is clear. We see that the nth coefficient, a subscript n, is equal to the nth derivative of the function evaluated at x equals 0 divided by n factorial. And so we can now use this general result for the coefficients to rewrite our original polynomial expression. By substituting in the expressions for the coefficients, we arrive at the following general form. And this is exactly what we were looking for. This is the Taylor series of f of x about 0, also known as the Maclaurin series. Okay, so let's see what happens if we apply this to sine of x, the function we looked at earlier. Well, the first step is to define our function, so we write f of x equals sine of x. We then calculate the first, second, third, and so on derivatives, and that continues the pattern. Then we evaluate each of these at x equals 0, and we find the following results. We see that they cycle between 0, 1, 0, minus 1, and if we kept going with higher order derivatives, we would see that that pattern just repeats. Now, if we plug these values into our Taylor series formula for sine of x, we find the following blue expression. And this simplifies to sine of x equals x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on. Now, this isn't just an approximation. This infinite polynomial converges exactly to sine of x for all real numbers. And we can get a sense of how this works by plotting how our approximation improves as higher order polynomial terms are added, as you can see in the updating plot. And it was Euler, with his remarkable intuition, who saw in this expansion the glimmer of a connection between infinite series and geometry, between analysis and pi. And that insight, as we'll soon see, was the key that unlocked the Basel problem. What mattered most was that Euler now had a representation of sine of x as an infinitely long polynomial. And that gave him a clue. He began thinking about the properties of polynomials. First, the finite kind, and then, with characteristic boldness, he leapt into the infinite. Euler knew something simple but powerful. Consider a polynomial of degree n. It will have n roots, which we'll call a, b, c, d, etc. If you recall, this simply means that if you plug any of these values into the polynomial, the result is 0. Now, Euler also assumed that his polynomial satisfies the condition p of 0 equals 1, because in this case, it's possible to factor the polynomial and write it in the following elegant form. This factorization expresses the polynomial entirely in terms of its roots, a product form that turns out to be the key to everything that follows. Now, this may not seem immediately obvious, but we can show that this factorized form makes sense. If, for example, we plug in x equals a, we see that the first term becomes 0, and as a result, the whole product is equal to 0. Furthermore, if we plug in x equals 0, then we see that every bracket becomes equal to 1, and therefore the whole product is going to be equal to 1, satisfying our condition that p of 0 equals 1. So far so simple, but then in a leap of faith, and with the boldness of a young man guided more by intuition than formalism, Euler asked a remarkable question. What if a similar factorization rule held for infinite polynomials, just like the infinite polynomial we saw for the sine function? What followed was something that feels more like magic than mathematics. And as I walk through the next steps, you'd be forgiven for thinking, what on earth does any of this have to do with the sum of the inverse squares? But when all seems lost, just as we teeter on the edge of abstraction, Euler pulls a rabbit out of the hat, and the mathematical world erupts in applause. It's time to see the magic. Euler began by defining the following curious infinite polynomial function, which has the property that f of naught equals 1, mirroring the condition p of naught equals 1 we needed earlier for factorization. At first glance, it seemed like just another series, but then Euler made a clever move. He rewrote the expression in the following form, multiplying and dividing by x, which doesn't change the expression, but reveals something crucial. Because if you multiply out the bracket in the numerator, you end up with the following expression. And we immediately notice that the numerator now takes the form of the Taylor series expansion of sine of x. In other words, Euler had realised that his seemingly abstract polynomial was in fact equal to sine of x over x. And this was a key step, because now Euler could look at sine of x divided by x not just as a function defined by an infinite series, but also as one that could potentially be factorised using its roots, just like a polynomial. And that comparison between two completely different ways of expressing the same function would soon lead to one of the most beautiful results in all of mathematics. To see this, we set our infinite polynomial f of x equal to 0, and since f of x equals sine of x over x, this means solving sine of x over x equals 0, which is equivalent to solving sine of x equals 0, provided x is not equal to 0. Now, that's a familiar equation. We saw earlier that the sine function equals 0 whenever x equals 0, plus or minus pi, plus or minus 2 pi, and so on. So if we exclude x equals 0, we find that the roots of our function are given by x equals plus or minus pi, plus or minus 2 pi, and so on. And now comes the key insight. Euler now had a function, polynomial-like in structure, for which f of 0 equals 1, and for which all roots were known. And these are precisely the conditions which, in the finite case, allows us to write a polynomial in factored form as a product of terms involving its roots. And so Euler, with the boldness of youth and genius, wrote f of x in fully factorised form, just as one does with finite polynomials, using the roots of sine of x over x. We can then tidy this up a bit, and finally, we note that if we multiply out the first pair of brackets, we get 1 minus x squared over pi squared. If we multiply out the second pair, we get 1 minus x squared over 4 pi squared. And if we multiply out the third pair, we get 1 minus x squared over 9 pi squared. And we can continue doing this with each pair of brackets. And so we can now write f of x as a product of such terms. And this is where Euler takes a bold leap of faith. He said, I don't care that the right-hand side is an infinite product. Let's imagine multiplying out all the brackets, just as we do with finite polynomials, and gathering terms according to their powers of x. Start with all the ones multiplying each other, that gives 1. Then gather up all the x squared terms, each one comes from picking the x squared term in one bracket, and 1 from all the others, and do the same for the x to the 4 terms and so on. And if we do this, we get an expression that looks like a standard polynomial, a constant term plus a term in x squared plus a term in x to the 4 and so on, except now the coefficients involve infinite sums. And here's the crucial point. We now have two different expressions for the same function f of x. On the one hand, we have it written as above. On the other hand, we already had an expression for f of x from earlier, the function Euler initially defined. Now, for these two expressions to be equal, the coefficients of each power of x must match. And when Euler compared the coefficients of the x squared terms, something extraordinary happened. First, he got rid of the minus signs from both sides and wrote 3 factorial as 6. Then he noticed that every term inside the bracket on the right-hand side contains a factor of 1 over pi squared. And so he was able to pull out this factor and end up with the following expression. And now the magic trick reaches its climax, because the terms inside the bracket are none other than the sum of the reciprocals of the square numbers, the very series Euler had been chasing from the start. And if we multiply both sides by pi squared, we end up with the truly jaw-dropping result that the infinite sum of the reciprocals of the square numbers is exactly equal to pi squared over 6. A problem that had stumped the best mathematicians for decades was solved. Euler had announced himself to the world. When Euler first published this result in 1735, it caused a sensation. Not only had he solved a problem that had defeated the greatest mathematical minds, he had done it with a method so bold and unexpected that it seemed almost like sorcery. But he didn't stop there. Euler was able to use the exact same trick that had unlocked the sum of the reciprocals of the square numbers to tackle higher order sums, like the sum of the reciprocals of the fourth powers, and then the sixth powers, and he didn't stop there. He pushed further and further, finding exact results for higher and higher powers, all the way up to the case where the powers reached 26, a staggering achievement. But here's the twist. What about the odd powers? They're just as easy to write down, but here's the shocking part. To this day, no one, not even with the full power of modern mathematics and supercomputers, has found a simple closed-form expression for these sums. No neat formula. After centuries of effort, these numbers remain stubbornly mysterious. And in trying to make sense of them, mathematicians realised that all these sums, even powers, odd powers, and more, are part of one vast mathematical object. The Riemann zeta function, which we can write in the following form, where s tells you the power that the reciprocal numbers are raised to. In this notation, we would say that zeta of 2 is equal to pi squared over 6, and zeta of 4 is equal to pi to the 4 over 90, and so on. This single function sits right at the crossroads of number theory, analysis, and the deepest mysteries in mathematics. Its properties are tied to one of the most important unsolved problems of our time, the Riemann hypothesis, a question whose answer could change mathematics forever. It remains unproven, and there's even $1 million prize for the person who can crack it. But for now, that's the end of our story. Until next time. If you've enjoyed the beauty and elegance of Euler's work and would like to further develop your math skills, Brilliant is the perfect place to start. Brilliant is a learning app that helps you think more clearly and solve problems more effectively with thousands of visual interactive lessons across maths, science, programming, data analysis and more. You'll learn by doing, exploring concepts step by step, testing your thinking and building understanding through active problem solving, a method proven to be up to 6 times more effective than passively watching lectures. If you enjoyed today's video, I highly recommend their calculus course, which covers differentiation, integration, and related topics that build on what we've explored today. It takes these ideas and makes them intuitive, with clear visuals and interactive challenges you can experiment with. You'll see how the concepts fit together and gain tools you can apply to your own mathematical discoveries. To learn for free on Brilliant, go to brilliant.org/physics explained, scan the QR code on screen, or click on the link in the description. Brilliant's also given our viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. And as always, a massive thank you to all my patrons, and a special shout out to the following, who have been incredibly generous with their support. Thank you so much. I couldn't do it without you.